All right, how's everybody doing? Hanging in there on election night? Biting nails, I'm sure. All right, so let's get going. So don't tell the results. Yeah, waiting for the world to change. Yeah, we'll see what happens. The audio is poor. Can everybody hear me all right? Yeah, okay. Helene, you might want to check your audio. I'll speak as close as I can. So tonight I'm going to talk about resilience. I know this has come up with one of the classes I'm doing right now. I mean, it's a topic that we talk about a lot. I wanted to dig into it because I think some of it may not be clear, and also people talk about it a lot, and sometimes they don't define it. So the topic is resilience and multifaceted content. And I actually prepared slides for tonight just because it's hard to normally what I do obviously is I go through and I send in links as I talk, which is fine, but this is I find these concepts visual. It helps to see graphs and stuff like that to understand how these things are working. So that's why I've prepared these slides. And plus, I'm going to talk about some of the work that I've done in the past that that's visual, right? So anyway, let's get going. You will see what I'm talking about. Just one sec. Share files. Okay. First slide here. Resilience. So what is this idea that we're talking about? I'm going to first talk about it. Just a sec. I want to see if. Okay, good. Keep your chat open. Good. I want to talk about it in the context of first Amazonia. Now, I think some of you may have heard about my Amazon work before. If you have, this will be kind of you hear about it again. But for those that haven't, then this is going to be a good demonstration. Regardless of whether you've heard it or not, I think it's worthy. It's a very good example of breaking down this whole resilience idea and something that actually you can see, feel, understand, and so forth, and then we can relate that to socioeconomic. So I want to talk about the ecological resilience idea and explain how you analyze it, and then kind of say, well, how does this relate to socioeconomics? So we're going to start with Amazonia. So I did a few years worth of work in Amazonia looking at ecological resilience of Amazonian ecosystems to whatever it is that disturbs them. And that's the first thing you need to think about when you do resilience studies, is to frame your question properly. And the question one should ask always when you're starting out, like say for instance, if you got hired by a company and this says, look, we really want a resilience strategy, the first thing I would suggest that you say to them is, okay, well, that's fine. I can help you out. I know, I studied at Rural Roads. I know a bit about this whole idea, some good references and stuff. But I need to understand what you mean by that. And typically when I'm working on this stuff, this is me saying to these people, for you, I say resilience of what to what? Like you want me to analyze and develop a strategy for resilience of what to potentially what. And so in that case, probably what they might be thinking of is resilience of that company to maybe some economic troubles, regulations, climate change, whatever, But you need to start there, and then you can start to frame, your analysis. So in the case of Amazonia, we have tropical forests in the Amazon that are affected by timber harvesting, pasture conversion, drought, and fire disturbance. Those are some of the major things that occur in that region. So that's the resilience of Amazon to what? Well, it's to this. It's to droughts, fires, and land conversion. The goal here was to assess spatial patterns and ecological processes that respond to those disturbances, like critical ones. And then also look at this in the context of the Earth system, because tropical ecosystems, they're a critical part of the Earth system. If you want to look at how the global processes work, they're a very buffer of energy, water, and carbon. So there's a lot of carbon exchange that happens between the Amazon and the atmosphere. Like it's a big, you know, it's a big sink, a big whack of carbon sitting there, as well as energy and water, lots of water coming in and out of that ecosystem. So currently, like in the last couple of years, this has exploded again. It's quite a hot topic because we had those fires a couple of years ago, high number of fires and smoke, like we had in British Columbia a couple of years ago. The smoke drifted into Sao Paulo. So you had Sao Paulo with very smoky sky. And so if you're not familiar with the geography of Brazil, it's a huge country, right? It's like massive. And so Sao Paulo is at the bottom. It's the southernmost, well, not southernmost, but very far south. And the Amazon rainforest is quite far north. So it'd be like us getting, I don't know, some impact from the Arctic in Canada and down in Vancouver. It'd have to be something pretty darn big for us to see impacts in Vancouver, considering the spread geographically. And that's what happened. Those fires, there's so many of them in the Amazon that the atmosphere in Sao Paulo was noticeably impacted. Hence, people start to think about it. So it's about 5.8 million kilometers squared, and in the Amazon, you have Peruvian Amazon, Bolivian Amazon, Ecuadorian Amazon, but what I'm defining here, that 5.8 million kilometers squared, is the Brazilian legal Amazon. So it's maybe hard to see in this image, but it's this yellow. You see the state, the Amazonas, that's one of the states, but you have Pará, Mato Grosso, Rondônia, Goiás. Those are all different states in Amazonia. Acre is another one. And then this boundary around the edge, this kind of brighter yellow boundary, is what they call the legal Amazon. It's a humid tropical rainforest, but what's interesting in this system is that it's coupled. So we call it a coupled system, meaning that about half of the rain that's into the Amazon itself comes from the rainforest. So meaning like the rainforest evapotranspirates, and then that moisture goes into the atmosphere and the boundary layer condenses, forms clouds and condenses on condensation nuclei, and then condenses even more and rains. So that's why you get this, it's cycling of water from the forest to the atmosphere. And then we've got a bunch of land use challenges there as well. So deforestation is a dominant force. They call this region at the south here, you can see that this red part is, it's kind of like an arc in the southern part of the Brazilian legal Amazon. And that's called the arc of deforestation. In the past, some models have predicted up to 40% loss of forest cover by 2050 based on business as usual. So there's a lot, and now it's even worse because it depends on the government that's in power in Brazil. The pro-development governments tend to see more land cover change, whereas the more conservation-oriented ones have reduced that before. So the big concern here is actually ecosystem resilient. How resilient is this ecosystem to these disturbances, and then also to some other disturbances such as climate change and so forth. And so the real kind of the framework that we need to look at when we look at a problem like this is this ecosystem ecology framework. And so in ecology, I think I may have referred to this before, you have a bunch of different types. You have population ecology, you have community ecology and so forth, but an ecosystem ecologist looks at things as a system, a functioning system. So some people may look at this as a bunch of species, like frogs interacting with one another, whereas an ecosystem ecologist tends to look at these things, an ecosystem, more in terms of the movement of water, nutrient cycling, around through the plants and the soil. So ecosystem ecologists tend to look at how the biotic and abiotic components systematically interact, whereas landscape ecologists tend to look at the spatial distributions over landscapes. Population ecologists look at how populations interact with one another, okay? So typically in resilience, often, although the original theory was really based largely on populations, now a lot of the work occurs within this whole ecosystem ecology paradigm. So many perspectives. My perspective lands in the ecosystem ecology and landscape ecology camp, mostly because this is the most relevant approach for things that I work on. So like land cover change, climate change impact on lands, and vice versa. So one of the questions that I would ask, I did ask with this is, are there disturbance factors that would affect key support systems that could cause a significant shift? That's my resilience question here. So in this case, you know, obviously a couple of things you might want to think about, or what I would think about right off the bat are systems such as water, like the circulation of water, or nutrient cycling, if they get disturbed by a certain amount, will that cause there to be significant impact overall of the overall system function? So that's kind of starting framing my resilience question with that understanding. So in order to really get to the meat and potatoes of this, I don't think you always have to do this, but I'm a field-oriented person. So this is the landscape of what it looks like down there. So there's Salvador. I personally went there and learned Portuguese after doing it before I went to Brazil. Rio de Janeiro, Sao Paulo down here is where their space agency and so forth is. That's where I spent a lot of time with those folks. And then Porto Velho is the furthest, one of the most furthest parts you can go north into the Amazon, which is right in where Porto Velho is, without having to go by boat further. So I decided to see the land, take a look at the transitions and so forth, and then went by land from Sao Paulo to Porto Velho, got on a boat, then went up that river right to where the rivers join where Manaus is, and work with the field scientists at the LBA project. Okay. So I found a boat. Now this is interesting. So another key thing that we need to think about when we're trying to frame a resilience problem, because a lot of this stuff can be quite abstract, right? Like you want to look at, oh, well, what is a system? You see all these diagrams of graphs and thresholds and equilibrium diagrams, but you know, I was really keen on seeing the land and seeing what stuff looked like. And part of that was going and also understanding who lives on the land and getting a feel for the people. And trust me, that's the thing I remember the most is the people and the landscapes I saw. So I got a large boat from Rio Madeiras, or from Porto Velho along the river that goes northeast from there, which is called the Rio Madeiras. And it was supposed to be a 3-day ride, but it ended up being 5 days. A large boat filled with people, like 100+ people, that involved a lot of music, dancing, friends, and Amazonian cowboys along the way. But what it also involved was observations, okay? And this is where it gets into, like, how do we really start to see this stuff? And one of those observations, as I mentioned before, on every day of that trip, what I tried to do was get up quite early and see what was going on in the atmosphere. So I mentioned that we have atmosphere-biosphere coupling. So what is that, right? So I observed what was going along the river and the interface of the forest and the atmosphere. So you can see in the shot here, we have the Rio Madeiras, and it's at 7:10 a.m., and that's July 8th, 2006. That's a long time ago now, and that's when I was doing this work. So what do you notice there? I mean, it's clear. So 7:10 a.m., so there's not, sun has just come up, you know, a couple hours ago, or not even like an hour and a half ago, and things are pretty stable, right? So if you then look at 1 p.m., same river and just further downriver, because we're traveling in that direction, you can see there's clouds starting to form in the lower atmosphere there. So why do you think that's happening? Like this is up, what's going on there? Do you think those clouds just got transported in? Yes, exactly, Norm. It's evaporation. It's evapotranspiration. So there's evaporation and transpiration happening. That's moisture that is coming. The trees are not creating the condensation nuclei. The trees are doing what they do. They're absorbing photosynthetically active radiation and photosynthesizing, therefore releasing water vapor into the atmosphere as part of their photosynthetic process. So they're releasing water vapor. When that water vapor goes up into the atmosphere, what it does do is it condenses. The water vapor will condense on condensation nuclei. So condensation nuclei are the things in the atmosphere that water vapor will condense on when the pressure and the temperature is appropriate. So if any of you take ecology, then you understand how all that stuff works. So you need condensation. Yeah, it's first year meteorology. You got to go to meteorology. So you need the condensation nuclei, which are often particles or whatever, and then you need the water vapor, and together that's what forms clouds, right? And then if enough condensation happens, that's when it starts to rain. So you can see in this 1 p.m. there's starting to be some clouds there, but then come 6 p.m., look at that. It's downriver some more, but you know there is some serious condensation and upward momentum happening there. With the right, with what results in cumulonimbus clouds. So basically, that cloud there is just shooting water vapor and into high up into the atmosphere, which will condense and condense and condense. And believe me, if you're underneath that cloud, within like half an hour, you're going to get dumped on, right? I've been in those situations where it just like deluge of water comes down on you. So essentially, what that is this kind of atmosphere-biosphere coupling that I was mentioning to you, which is, you know, the relationship between the evaporation transpiration. So what does this have to do with resilience? Well, first and foremost, this is the classic definition, or one of the classic portrayals of what resilience is, where you have a state diagram. You have the resilience definition goes back to Hollings 1973. Excuse me, I'm sorry. Is in which it's the ability of systems to absorb changes of state variables, driving variables, and parameters. You can resilient to a degree, but then if it exceeds that, then there is a shift in state. So this framework of the resilience of a system may be dictated by certain conditions. You know, in this case, the amount of biomass might be one of those factors that would contribute to it, the temperature, precipitation, nutrient availability, and you can also see this in landscape patterns. But this diagram here, which is from a paper by Beisner et al., shows this kind of traditional landscape where you have a shift in variables which can cause that ball to go up to the threshold, but then go into the other stable state. So they'd be like a forest or not forest. In terms of human being, it could be I'm at a comfortable temperature, but then I get worked up enough that it caused me to then shift into a fever temperature space, right? That would be a resilience. And what we have in our body is homeostatic mechanisms to control for that, right? We get really hot, we start to sweat, cools us down, keep us within that one stable state, which is a comfortable operating parameters. Okay, so that's the traditional, one of the traditional ways of looking at it. Whereas, you know, my job with this project was to try and frame this whole problem in terms of what are the things that are impacting it? What is the resilience of what to what, right? So the problem in the literature was related to whether or not these rainforests in the Amazon could in fact shift to savannas if some of these variables that are supporting them or impacting them were to like reach certain thresholds, right? And some of those variables that I determined were this stabilizing system, which is in the top there, high precipitation and evapotranspiration, which is a negative feedback system. So a negative feedback system is something that sustains something, right? So like snow cover or ice cover is a negative feedback system because it reflects the albedo is high, so it pushes energy away from the earth, keeps it cold. And in the bottom, though, we have a positive feedback system. And fire, in this case, in the case of Amazonia, is a positive feedback system because positive feedback systems push a system to a point of instability. Like they will push it to outside, away from the state that it is in. So in the case of a rainforest, and potentially to the other alternative state. In this case, it would be savanna. So things that are driving the fire feedback process are the fueling of fire by standing biomass, and then also land use and deforestation. In addition to that, you have climate forcing, which is also influencing the fire feedback system. Okay, so with this is a state diagram. It tries to show that there can be a shift from a rainforest to a savanna if some of these factors aren't working properly, like say if the stabilizing negative feedback system of high evaporation, evapotranspiration, precipitation isn't working properly, if it's so it's becoming less stable, or if that fire feedback process, which is a positive feedback process, really gets amped up. So the more fire, the less stable this is, that the more it leans towards another state. The more more evapotranspiration or coupling, water coupling, the more stable this is. Do you understand? You see what I'm saying? This is how this system works. And you kind of have to frame things in this way if you're trying to kind of analyze what it might be. Now, back to the example of your company, you might draw this, okay, well, this is a healthy company, which is, I don't know, happy employees, good cash flow, whatever it is, those factors. And then an unhealthy company would be low cash flow, low morale, low employment, that kind of stuff, low innovation. So you want to pick those variables that are important for whatever it is you're looking at. So this is how I established this framework for Amazonia. So I walked through this just to reinforce that. The blue areas represent a negative feedback system. So about 50% of the rain comes from the forest, right? So keeping it a moist tropical rainforest depends on that negative feedback system. So this is similar to the homeostatic mechanisms that exist within human beings. The red arrows represent positive feedback systems that move the system towards instability, right? As things dry, fires start. Fires destroy the forest, and they also create smoke. Smoke inhibits rain from forming. Okay, so you get less rain, things become more dry, and therefore it becomes more, the probability of there being a fire increases, right? So it gets worse and worse and worse. Positive feedback system. Analysis, so that's neat. That's neat that you can kind of frame stuff like that, but then how do you go and analyze this stuff? And this is what we're going to talk about after. Well, I chose in this case remote sensing or satellites, where you can take aerial imagery taken from a satellite in space, which can tell you certain things. In this case, I looked at vegetation indices, which is basically how the land cover reacts to photosynthetically active radiation, whether it absorbs it or not. And that can tell you how green something is, how much photosynthesis is happening. So this is called MODIS. It's 1 kilometer spatial resolution. You have 16 and 30-day composites, fairly high spectral and temporal resolution, 36 bands, and then daily shots. So you get a lot of like imagery you can take, and allows to look at seasonal variation and interannual variation. So you have how things change between years and how things change throughout a season. That's a good way of monitoring how the forest is doing, or whether or not a forest becomes a fire or a degraded land of some sort. So I'm not going to go too far into the analysis, because I want to talk mostly about the concepts. I just did some transects on the imagery and then charted how the changes occurred over time. That was the best way to do it, I found. I also looked at precipitation, which you can get off radar. So this is from something called TRMM, Tropical Rainfall Measuring Mission, which measures amount of rain. So it's in millimeters. So I can see at fairly coarse spatial resolution, but every month I can get a shot and see how much rain there is throughout the Brazilian legal Amazon. So you can show the wet season and then also the dry season. So you can actually see that's the wet season. And then this is the dry season. So this is in July. And this previous image here is in March. Okay, so it's quite a big difference between the seasons in Amazonia. The dry season is pretty dry. See, so there's just no rain in parts of the Amazon in the dry season. And this is the thing that's concerning. So you can see that I'm trying to find some variables here that I can actually measure periodically over time to see what kind of changes occurred, and then ideally determine if there are thresholds that, if they are crossed, there can cause a shift, in this case from a rainforest to a savanna. How long was my sample period? Well, I chose 2000 to 2006. So the thing with remote sensing is you're kind of limited based on how long the satellite has been operating. So there's one called Landsat, which has been up since the 70s, but you don't get as good coverage with Landsat. It's coarser resolution, or you don't get as a daily shot with Landsat. It tends to be everything 18 days, because every 18 days you get a shot, and the spectral resolution isn't as good. So if you want to go back to 1974, you can do that with Landsat, whereas MODIS was launched in 2000. So that's the earliest I could get an image. If I were to do the same analysis today, I could do from 2000 to the present. So I would have, quite a bit of data. And I'm actually looking at that for a project right now. The thing is, though, with using MODIS, you get global coverage at 500 kilometer spatial resolution, and you have 2 shots a day, morning and afternoon, because there's 2 satellites at the same sensor. So it's sun synchronous, so you get a morning shot and an afternoon shot. The thing you need to worry about in the Amazon is cloud cover, right? often you'll get clouds that are covering the forest. So you can't see anything through a cloud on optical remote sensing. So what I did with this was I looked at every month, like that was my sampling period every month, and I just took the maximum value. So I took daily shots, but I did something called maximum value compositing, where I took the maximum value for each pixel across that whole month and made sure that, at least on every pixel, there was at least one clear day for that whole month. And that allows you to get, like, the common technique in remote sensing to get rid of cloud interference or whatever other interference you might have. So that's what I had, 6 years of one shot every month that was based on composites. So it was a lot of data processing, but I think the data is pretty good. I also looked at fires. So we have rain, we have vegetation, and we have fires. Those are kind of the three things I was really interested in if you looked at my model. So I looked at spatial pattern of fire, and fire can again be measured from space using thermal bands, so like the amount of heat that's coming off the Earth. So if it's beyond a certain threshold, you can assume that it's a fire, right? So the key question here, though, was to determine what was causing those fires. Is it in direct correlation with close proximity to the human settlements? Is there a relationship between where roads are to the fires? And there's a lot of literature along that. But there was, like, this is Mato Grosso, which is one of the southernmost states in the Brazilian legal Amazon. You can see then this image here. Now, this is fire frequency from 2001 to 2006, so that's over the whole sampling period. But you can see in certain areas there's a much higher frequency of fires, and those tend to be closer to the roads, okay? But as you know, there is a positive feedback mechanism between fires and the resilience of the system. So if we get a lot of fires, we could potentially see it, possibly pushing the ecosystems past that threshold and converting it from rainforest to a savanna. And that has actually happened in parts of Amazonia in the Northeast. Okay, so what's the data though? What does it look like over different years? Can it flip back? We'll get to that. I looked at this and I looked at between years, and this is an important piece of the analysis in relation to what happened recently, like last year with the fires in Amazonia. So you can see here that there's a seasonal pattern here. So the orange line there is 2001. That's for the fire frequency across January, February, March, April, May, June, July, August. So you can see there the dry season, right? The dry season is June, July, August, September, October, November. That's when it gets quite dry there. And you can actually see it in the data. If you're looking at time series of trim data, you can see it getting dry and then wet, dry, wet throughout the year. So in 2001, which is the orange one, you can see a traditional, and you would see the same thing in British Columbia. In the summer, we get a lot more fires. In the winter, we get less fires. So that's not common. But in 2005, which is the blue line, you can see that there was almost twice as many fires in the state of Mato Grosso than there was in 2001, right? So it was literally twice as much. So why do you think that is? What happened in that year? Could have been a lot of things. El Nino, close, very close. Drought. Yeah, it was a drought. So it was a drought that was induced from something similar to El Nino, though. This is a good point. It was a drought that was induced by something called the Southern Tropical Atlantic Sea Surface Temperature Anomaly, which is like an El Nino. It's an ocean oscillation, but it happens in the north-south direction rather than east-west, which is El Nino, and it happens in the Southern Tropical Atlantic rather than across the Pacific, Southern Pacific. And it does the same type of things. It's cyclical, and what it does is this warm body of water forms periodically in the Southern Tropical Atlantic, and it happened in 2005, in which it gets a little bit warmer on the surface in the Southern Tropical Atlantic, and that causes there to be a drought. Periodically, it happens over a cycle. And that's what happened in 2005, and that's apparently what happened again a year ago. Now, what's interesting, though, with this is, so we have to think about this because, okay, we can say, well, if this is cyclical, it's going to happen again. So we have to be prepared for this. And the question is, will this happen again to such severity that will impact the Amazon to cause it to shift, or some ecosystems to shift to a savanna? And that's the question. Another interesting point, though, was that when I look closely at that southern tropical Atlantic sea surface temperature anomaly, some of the colleagues that were doing work at Sepitech, which is their Met service, they're like their environment and climate change group for Brazil. They have modelers and so forth, and they did some work on that. And what they found was that the southern tropical sea surface temperature anomaly, that anomaly was getting stronger with higher concentrations of greenhouse gases in the atmosphere. Meaning, loosely speaking, as there's getting more climate forcing that is occurring as a result of increased concentrations of greenhouse gases, it's a stronger drought. We can expect there to be droughts that are stronger as a result, and stronger droughts will hypothetically lead to a higher frequency of fires, right? So this then leads us to think, okay, well, climate change is something that is impacting this. Now, not immediately necessarily, but certainly over a longer time period. So we need to think about that as a slower variable, okay? And so then I looked at the changes in states, like, well, when you classify an image and say it's like a savanna, a forest, or whatever. And what I found was between 2001 and 2006, there was actually a very clear shift of forests shifting to some sort of degraded land, like a savanna, I'm calling it. So the observed changes that I found were between those time periods, you didn't see as much afforestation or reforestation going from savanna to forest, but you had a lot more forest being converted to savanna. And that would be through agriculture, fires, or what have you. I mean, with remote sensing, it's pretty coarse. But there was a very clear pattern that over that time period, there was a shift in ecosystems. So this is the model once again. So we go back to say, okay, well, let's think about resilience now. We have to think, we know that there is climate forcing occurring. We know that we've got this negative feedback system. We have a positive feedback system, and then we have some other forces that are impacting the rainforest, such as fueling and land force and deforestation. Now we need to think about, okay, well, what then are these thresholds that we need to consider? And that's where some of the kind of the, you know, licking your finger and putting on the wall type of thing, like, you know, estimations take place. But you see what I'm saying? Like, this model makes a lot more sense when you start to look at it in terms of the data. Like, how many fires, for instance, would there need to be for that rainforest to shift to a savanna over a certain period of time? That would be one of the questions that I'd start to look at. Say, okay, what is that threshold, right? To what degree does evapotranspiration need to be inhibited before there is a shift from a rainforest to a savanna? Okay. Do I have numbers on that? No, I don't have the numbers. I have some ideas, but I haven't get to that level of precision with that. Like, it's pretty tricky with the number of fires. I think number of fires we could get at that. Evapotranspiration, it's a little trickier. Okay, so conclusions from that. There are others that have looked more closely at fires, though. Like, it's not that I'm not interested in that. With that particular project, I got to the point of seeing the major trends, and then, you know, you got to dig a little deeper in order to say, okay, what are these particular thresholds? So some indication that large-scale shift is underway, difficult to pinpoint specific linkages, right? Land use policy is definitely a contributor. So one of the things you can look at is the impact of roads. It's actually something that's quite measurable. You can say, okay, if a road goes in, to what degree does that impact frequency of forest fires and reduction in land cover? And it's actually pretty clear over time. You can see the impact of road versus no road. And clearly shows in the data that there is a pretty strong impact of droughts on the frequency of forest fires. Okay, so you have a general model that allows you to then, what would be the mechanism there? Where, with what? Roads, you mean? Yeah, roads is purely socioeconomic development. That's the main one. When you build a road, you create access. And in places like Brazil, when you create access, you create opportunity. So there are a lot of people. So this has been hired. Yes, absolutely. The BR-167, the Trans-Amazonian Highway, definitely higher incidence of fire because there's more access. So the roads create access and they create opportunity for people to go and settle land. And what people do, I mean, there's a lot. I don't know if you've ever been to Sao Paulo before, but there are a lot of people in Sao Paulo. So people often are actually even encouraged or incentivized. At first, back in the 60s, once they proposed the BR-67, the idea was to develop the frontier and to give people, incentives to go and move to the Amazon and then, develop and clear land and start a fire or whatever. So yes, you do see that when you see the highways that are built without legislation. So if it's just highway and there's no controls, you will see it. The highway is built in 1 year, and then the next year you'll see an increase in fires around the highway, and you'll also see this kind of it's kind of like a fish scale pattern, where you have the main road, and then little roads will form off of it, and then little roads off those. It's like a fishbone structure. But there's clear evidence of that, and there's a lot of literature around that too. So going back to this, Macron what does this mean today? So Macron's is, yeah, there's a lot of things that are associated with this. So this was from the news when this was coming out. Macron must retract insults for Brazil to accept G7 aid to help fight Amazon wildfires, Bolsonaro says. So you got a lot of this kind of like, look to our land, leave us alone. Then the rest of the world saying, look, the Amazon is the lung of the planet. We're going to like help you out in fighting the fires or what have you. So that gets into a lot of politics and so forth, the same with RED and RED+. But the nuts and bolts of it are, that's how it's actually biophysically working, is, like that kind of a system. So, but is this all there is to the idea of resilience? And I've kind of gone through this before with some of you. No, it's not. We've only scratched the surface, really. There is more to it. There's social and economic dimensions, as Norm was suggesting and as Nicolisa is suggesting. How do these other factors influence it, right? You can even tie to this problem the price of soy. So the price of soy, like soybeans, will factor into this problem, right? Because there's a tremendous amount of soy that is purchased by China, or has been in the past, that is grown in Brazil. And as the demand for that soy spikes, so does the fires and deforestation in Amazonia, because there's more of a demand for soy, therefore more land is cleared and so forth and so on. So it affects our resilience model. So definitely social and economic dimensions play a role in this whole idea of resilience. Okay, so how do you introduce these factors into it? Now, this is a diagram from the classic paper. So if you really want to get into this idea of resilience, I highly recommend you start with the beginning. So go to Halling 1973. There's a link here to that paper. This is a pretty trippy paper diagram. I just want to show you some examples of how you represent these things sometimes. So this is from Halling's paper back in 1973. So Hall was a ecologist, more of a population ecologist at first, actually. So he dealt a lot with Lotka-Volterra models, how like populations of species interact with one another through like predator-prey relationships and then fecundity and all that kind of stuff. But this paper is the paper. This is the start of ecological resilience. Like anybody that works in this field knows that this is the one that's always cited. So Buzz Halling wrote this paper, and I'm just going to show you some diagrams. And he essentially framed this kind of multiple states and how those states, what his idea originally though was looking at species populations. He was really focused on species, particularly fish, cod populations and so forth. So Atlantic cod population collapse is a good example of a resilient one. They were harvested beyond the point at which they could recover as a renewable resource. Back to Nicolisa's point about whether something will bounce back. In the case of the cod fishery, it didn't bounce back, whereas in other cases it can. And this is part of the thing that the process of analysis you have to go through. So if you look at this here, you will see that he's looking at the relationship between over time. So time is in this, it's in the x-axis, And then you've got, try and view this in 3 dimensions. So you've got like, this is like, look at this like it's a square, a cube, okay? So you've got one surface at the top of the X population, you've got the Y population at the bottom, you get then the time dimension over on the X there, and you can see over time how that X population, so that could be, I don't know, hyenas and something or other, I don't know, or I don't know, what would be a good one, what eats what, seals and fish, right, or whales and seals. So you can see that this population here, no, this gets pretty crazy. Like this is the interesting part of ecology, like looking at the relationship mathematically of all these different things working together. So you can see here that this population fluctuates over time, and then this population fluctuates over time, and then you have this diagram on the left here, which is a relationship of the state of both of them and how they relate to one another. Okay, so you can see obviously if it's a predator-prey relationship, you can see that as one goes up, the other one is going to go down, right? Because more predators and less prey. So that's the early renditions of how do you reflect this kind of these relationships between different variables in an ecosystem over time, given certain dynamics, right? And then you could add on top of this like biophysical things if you wanted to. But his early work was largely on the interactions between populations. And like, if in this case you would add to that fishing, like, you know, the predator would be, you know, fishermen, because you're, you know, impacting the population. Okay. So then you can start to frame things over in various types of reproduction curves and the relationship between fecundity and mortality. So if you get like death and fecundity, birth and death equal to one another, that's like an equilibrium state, right? So you can see that in certain populations, over time, you can see multiple equilibrium states reached and so forth. So this is kind of this world of population ecology and resilience, right? You look at the relationship between predators, prey, birth, death, and maybe throw in some other biophysical parameters, and then come up with a model that would represent what's going on with species. Okay, that's like 1973 version resilience type of stuff. Look at the paper though, I'd recommend it. So that's how like the early work was done, and then I've shown you some of the later work that's more like ecosystem ecology type of stuff, where you look at biophysical parameters. Like I don't look at species in my work. Like I could care less about who's eating what there. I want to look at the water, the energy, and the fires, and that's the major factors I was interested in. I was not interested in how many lizards were these other things. Okay, but so the question I'm trying to get at here in the latter part is, how do social and economic factors get introduced to this system? It's already complicated enough, right? Well, we need to factor in economics, and we need it to be linked with social and ecological systems. So this whole idea of socio-ecological resilience comes into when we start to think about what are these social factors that are in interplay with ecosystems, like, for instance, building roads and creating fires. That's a socio-ecological system. Development pressures on ecosystems resulting in fires. So this is a really good paper that I'd recommend you take a look at, and you could get access to this if you're a road student, or if you want to email me, I can probably get you a copy. And it's by Farley and Voynef. It's 2016, so it's a newer paper, and this is where a lot of the more interesting work along these lines is. Didn't really happen much in 73, because that was just the early stages, whereas now we're very aware of the close interactions between social, economic, and ecological systems, and the need for linking them together. So this paper is entitled Economics, Socio-Ecological Resilience, and Ecosystem Services. And what they tried to do with this was examine the relationship between economic thinking, socio-ecological resilience models, and then also ecosystem services, and trying to find ways to kind of balance these things out and what are the predominant themes. So these are some highlights that they pulled out of this paper. Current economic activity appears to exceed critical socio-ecological thresholds, which I think is, you know, we have a tacit understanding of that based on our work. Economists generally assume that technological innovation and the rules of economics, meaning the relationship between supply and demand and pricing, will ensure growth and resilience, that we can innovate our way around limits to growth, for instance, and that the nature of economics will take care of us hitting the threshold of the limits on are the three pillars being replaced in the mainstream. We'll get to that. We'll get to that. Panarchy theory. So this is something that might be new to you and will be introduced and explained in this paper, and I'd recommend taking a look at this paper. Panarchy theory suggests that continued growth promotes irreversible collapse. And panarchy theory is something, again, that Buzz Halling and colleagues came up with, which is this kind of figure-8 loop of development, which seems to be prevalent in social and ecological systems, that they continued growth ultimately leads to irreversible collapse in both ecosystems and social systems. They also found that, excuse me, I hit a threshold there, that economic degrowth, so this whole idea of economic degrowth can be a means of planned release, can help to restore social and ecological resilience. So you don't get to that point where there is this irreversible collapse, rather you engineer an economic degrowth. Panarchy example would be, yes, exactly. Panarchy could be used in the collapse of the cod fishery because you had, I'll give you some other examples off the top of my head. I'll think of some other examples. But that's a good example. You had harvesting, people made a lot of money in the cod fishery, like there was a heavy boon on economics there because of the overfishing, but ultimately that resulted in a collapse because we went past a critical threshold. But this whole economic degrowth, which is a strategy that they suggest, planned release, can help to restore social and ecological resilience. We can get into that a bit. And then lastly, they suggest that open access to information can stimulate appropriate technological innovation, which they do stand by the fact that technological innovation is one strategy or means by which we can work with thresholds that we're confronted with, right? And that's not a myth. That's a well understood phenomenon. So the crux of our argument here is that our economic system takes energy and materials in order to operate, right? So the way we work our economies requires inputs of energy and materials, and those have to come from somewhere, right? That energy and materials has to arrive from some place. They don't materialize out of nothing. And this has a toll on ecosystems. And so if you want to look at this from a macro standpoint, you can go and look at the planetary boundaries model, which is a global macro look at the impact we're having globally on key life support systems that they're calling planetary boundaries for the planet, such as biodiversity and ecosystems, nutrient cycling, atmospheric stability, et cetera, et cetera, et cetera. But what is driving a lot of those impacts, say for instance the impact on nutrient cycling, is economic activity, agriculture. So the impacts of fertilizers and so forth and land cover change for agricultural production is really impacting dramatically that planetary boundary for nutrients. Now, although some of these resources are renewable, right? So renewable energy, for instance, or even forestry, for example, is a renewable resource, we still live on a finite planet. So this whole idea of us being in a closed system and that some of these boundaries that we're coming up against are based on the fact that we live on a finite planet. So we have to be aware of these thresholds that may exist and whether or not we're crossing them. And if we do cross them, back to Nicolese's point, if that's a reversible or non-reversible threshold that we have crossed. Now, cod is a good example because we crossed that threshold in terms of how much we extracted, and it didn't really recover, marginally, but not significantly. It was really, a one-way path. So an example here is in terms of our energy uses. This is why it's such a critical election down south, and while these decisions we have about climate change are really critical ones we need to ask ourselves right now, is because even still, roughly 82% of the energy consumed globally is from finite stocks of fossil fuels. Those aren't renewable energy sources, right? Like hydro or renewables like solar, wind, geothermal, et cetera, et cetera. So we're still really very much entrenched in a paradigm of consumption of finite resources when we are confronted with planetary boundaries that we are pressing up against. That is the situation we're in right now. Okay, so ecological changes, right, as we described. So I went through those in Amazonia, and those that same kind of idea around the impact on ecosystems, which collapse and so forth, can be looked at on a variety of different circumstances. Species populations like cod, water quality in eutrophic lagoons and lakes, whatever, whatever ocean acidification, they have coral, blah, blah, blah. We can see a lot of different examples that you can look at ecosystems and whether or not those changes are reversible or not, and the changes that ensue as a result of impacts of development. Now, socioeconomic changes we haven't really touched on, but I'm just going to go over to this briefly, is these are the thresholds that they have identified in this paper, and there are likely more, but these are the key ones that they identified, is that one threshold they identified is that when there's a smooth change in a quantity of a good or service and has a profound impact on individuals or the economy as a whole. So for instance, one of these smooth changes is the amount of food intake reduction, so a famine, for instance, or a reduction in a caloric input to society overall. Again, that would be a famine situation. And that's, we've seen that. Those kind of threshold changes you can see in places like Darfur, or back in the 80s in I guess it was in Ethiopia, where they had famines in Ethiopia. Sudan, well, this is the good example is Sudan. Right now, and I'm going to show you some images in Sudan in the next one. Another one change here is the rapid reduction in fossil fuel consumption, which is another socioeconomic change, has been shown to cause recessions. And if it's a fast reduction in fossil fuel consumption, can ultimately result in economic collapse. Okay, so that's another variable that we look in socioeconomic systems that is something we need to observe and monitor. This is what I want to get at, the key takeaway here. So these are some images here from Sudan, from Darfur, of the situation there, and the reality that some people are confronted with there. So marginal slow changes in caloric intake can have pretty significant impacts on society when they're that close to sustenance. Okay, a second threshold that they identify in this paper is a runaway positive feedback loop in the financial sector. Okay, so these are things such as bubbles and busts. So like, say, subprime mortgages, increased fabricated valuations, like say in the dot-com era, where you get like the values and money and value created rapidly, and unsustainability without, it's a bubble, it's manufactured, it's fiction in a way. So these bubbles and busts, as a result, like we saw in the 2008-9 financial crisis, which was driven by subprime mortgages, can cause interruption in credit, which essentially is the lubricant in capitalist societies. We need capital to flow. So a financial crisis can inhibit the flow of credit, the flow of capital, which can be catastrophic for economies. So it's one of those resilience factors we need to think of when we look at the economic dimension or socioeconomic dimension of this problem. And then the third threshold that they talk about is major technological breakthroughs. Okay, so this is an example would be the Green Revolution, fantastic breakthroughs in agricultural technology and the use of fertilizers, nitrogen fixing technology. The transistor, right? And transistor is a very good example of a technological breakthrough that has really kind of allowed us to develop disproportionately to what we had thought we could before that economically, right? So ecologists tend to worry about reaching ecological thresholds. The internet, for sure, like social, artificial intelligence, right? Quantum computing potentially. So these are all innovation-oriented thresholds, and those are positive things from an economic standpoint. We get some of these breakthroughs, and they unleash wealth creation and value creation, like you see. Look at the value in the FANG in the FANG stocks of Facebook, Amazon, Netscape, and Google. Like, I mean, the sheer amount of value in those, for companies that are fundamentally based on technological innovation is astounding, right? So the idea there is that this kind of technological innovation and so forth can allow us to break through some of these perceived thresholds in the economy, right? It's a threshold that can unleash wealth, if you will. So ecologists tend to worry about reaching ecological thresholds. So examples will be climate change, eutrophication of lakes, maybe the Dust Bowl back in the, I guess, 1930s and 40s, where what we're facing right now is a threshold of degradation of biodiversity, for instance. So we worry about that stuff. Ecologists are like, look, we don't want to get to these thresholds, right? Because that maybe may get a cod collapse, right? There could be collapse, like the Amazon. I mean, do we want the Amazon to collapse? Because it's kind of looking like if these droughts get more severe, it might be a big problem. Economists tend to think innovation in technology will allow us to surpass thresholds, right? So our ecological thresholds in agriculture, screw that, we had the Green Revolution. We can grow twice as many crops on this land as we could before. So the question is, who's right? Right? Who is right? Is it the ecologists or the economists? When you think about, like, we got to be aware of ecological thresholds, and the economists need to be, let's go for these innovative ideas because that's going to blast us through any thresholds that we're faced with, right? I mean, this is where you get this kind of conflicting perspectives and paradigm. Well, neither is really right. They both have legitimate concerns. That's the thing, and they're based on their body of knowledge. So it's the role of both the ecologist and the economist to identify where we should be concerned. That's really where the strength of both those schools of thoughts comes in, because the ecologists and environmental scientists like us should be able to credibly identify the problems that are on the table and then say, look, we need to be aware of this, man. We shouldn't be pushing the limits on our cod fishery. We shouldn't be pushing the limits on climate change and the impact on some of the lands from a macro standpoint throughout the world. We shouldn't be pushing the limits on whatever, water quality, if you will. And then whereas the economists should be like, look, we should be investing in this area in research in AI because this could be the next threshold in how we go about doing things, which will unleash, economic activity and economic wealth and social well-being potentially. So pointing out where those critical thresholds are allows society to point in the right direction. That's really what I'm trying to get across here is we need to use both schools of thought to understand both the ecological reality in which we live and then also the fundaments of the economic activity that underpin our economy and our activities and then allow us to exist within those boundaries. So the question is, how do we then balance these imperatives? Back to Norm's initial point. Does this mean we replace the three imperatives, social, economic, and ecological imperatives? No. We take that body of knowledge and we integrate it together using these kind of like models, like a resilience model or a panarchy model. Say, okay, well, this is a situation in this given context, and then how do we manage ourselves and how do we balance these different imperatives? So we need to know where we are having environmental impacts and how to reduce them. That's one thing we need to know. And we also need to link those to the economic activity that is driving some of those impacts. Okay, so, and part of that, and this is what those in 322 is what we're dealing with in this unit, is dealing with the economic imperative. And one of the issues that we have to confront, especially as environmental specialists, is the idea of externalities. So if we know these thresholds, how do we manage our economic activity? Well, we know that we don't want to breach those thresholds, but we need to understand what these externalities are, because breaching these thresholds, such as CO2 emissions in the atmosphere or nutrients that have run off from large-scale agriculture into our water supply and so forth and so on, we need to understand what these externalities are. These externalities are unaccounted for impacts on the environment that result from our economic activities, right? So in agriculture, if we're going and growing potatoes and cotton and whatever else, and cotton for clothes and potatoes for food and corn for bioethanol and all that kind of stuff, in growing that and developing those resources, I mean, there's going to be impacts on other things, one of which would be impacts on water quality, right? So we need to be aware of that because if we don't account for the externalities from what we're trying to achieve, like say supply energy or supply cotton for clothing, then we are not seeing the whole picture. So environmental monitoring allows us to know about what these critical thresholds are, both from a global standpoint and a local standpoint, but the impacts that can push ecosystems to different states also need to be known. So we need to know what those impacts are that could potentially push us beyond those critical thresholds, right? So this is where TEEB, as you'll read in this unit, comes into effect, where we look at, okay, well, economics isn't just about production and supply and demand and so forth. It is also about the use of materials and energy to produce what we need to use for our economic activity, and that also means making nature's value visible, which is the tagline for TEEB. Traditional neoclassical economics just assumes that anything that is a factor of production going into economic operation we don't need to understand what these other things are. Whereas if we factor in the ecological reality and the thresholds we're up against, we need to understand what those externalities are. We need to account for them. We need to put the economic tools to work on them. Otherwise, they'll just go unchecked, like it's a free-for-all. So we still, however, though, so that means like putting a price on carbon, for instance, is a good example, or understanding the amount of water that's used in order to produce a pair of jeans, or et cetera, et cetera, et cetera. And then having an idea of what that full environmental impact is of products and services that we consume in our economy, and therefore where that then would put us in terms of the impacts on those thresholds and whether or not we're approaching those thresholds. So that is kind of like a rough breakdown of what these different factors and way we need to look at these things. But even given the fact that we start to consider externalities, we still need to appreciate the dynamics of impact, decay, collapse, and regrowth of this panarchy cycle here. So, and we need to manage these dynamics. So this here then in the top is the economy, and you can see how you can apply this in any given context. What they're trying to show here is multiple subsystems within an overall economy. We have this panarchy loop, which is the process of exploitation, conservation, release, and reorganization. It kind of circles along that line. So inevitably, it seems, in terms of the panarchy literature, we go through these processes, right? And sometimes we go through it to a point at which we don't return in the same way we went in the first place, right? If we've crossed certain thresholds. But the idea that they're trying to get across in this paper is that it's inevitable that we're going to get to a point of release and collapse. And whether or not that release and collapse is catastrophic or not is up to us, right? It's a policy issue, meaning that we can plan that release, engineered release, right? So in the case of, from an economic standpoint, looking at managing those bubbles, right? Making sure that it's not a collapse, rather it's an engineered release. That's what their argument is, and part of that can be done through technological innovation and just good policy and planning. So this is something to nibble on to start with, and I would encourage you to take a look at this paper if you have some time, just to get a bit more familiar with some of the details, because I can only go so far into it in an hour. But what it does give you, I'm hoping, is an overview of how the ecology system, like from a resilience standpoint, how you'd look at an ecosystem, a social system, and an economic system, and start to put them together, at least schematically. And then excuse me, and then dig into them and get the details that you need to monitor, the actual specifics. Like in my case, I was looking at, well, I need to look at water, vegetation, fire frequency, or whatever. And if you were to look at this kind of model in your community, you likely would choose other variables, right? Maybe there were some, I don't know, ecological indicators that you would look to, and some socioeconomic indicators that you would look to as well, but try and construct it in some sort of resilience model that made sense, okay? There we go. So that's your, I'm talking about the Farley and Voynov paper, correct? Yeah, that's the paper I suggest you take a look at. So here's the link. I'm just gonna go back, I'll put the link through. Here we go. I don't know if I can copy this. Okay, just one sec. Yes, correct. So Halling was one of the originators of panarchy theory, which is then used by other people. It's used by these folks. Just a second. Here we go. So I'm gonna. Okay, I don't know if this is going to allow you to get the paper or not. But if you're in the RRU library, can try that link. If you click that link, do you get the paper? I'm not sure if you might not, because I think I don't know, I'm on UBC's library right now. You need access. Okay. Well, what you can do for Royal Roads, just go to Farley and Voynov 2016, or this, yeah, that'll give you the abstract. So for Royal Roads, you go to the library website, online, and you take Farley and Voynov 2016 or Economics, Social, the title, search on that, that'll get the PDF. It's in, what journal is it in? It's Journal of Environmental Management, so it's not like science. So I think this is available, I'm pretty sure, in Royal Roads. In fact, I'll just look right now. Just one sec. I'm going to make sure that I have this. Yes, you have it in Royal Roads Library. So if you go to Royal Roads Library, search for that title. Here, actually, view full text. So yeah, you log into the RU library and you will arrive at that. Okay, so that title, Google that RU library, you'll get the paper. So there you go. I mean, that's anybody questions? Does that make a bit more sense? I know it's complicated. There's a lot of like abstract things and so forth, but I wanted to pick out a few different concrete examples that can allow you to start. Is desperation the mother of innovation? Will the tipping point be reached before the real pressure to innovate is upon us? I don't know. It's hard to say. I mean, it didn't work for cod fisheries, so I'm not an overly optimistic person. Like I am not. Sometimes I think it needs to get really bad before people do something about stuff. And sometimes it's enough time, and sometimes there's not. And that's where understanding ecological thresholds, I think, is something really important. I think honestly, humans tend to need a catastrophe to really, burst through stuff. At the same time, like, I have a lot of faith in human creativity and ingenuity. So that threshold that the thresholds that economists that have identified as innovation and technological development as it can unleash potential, I do stand by that. I will Sapiens. Yeah, I haven't read that book actually. It's on my list. I do believe that we have a lot of potential, humanity, in terms of our creativity and capability. Whether or not it's fairly distributed and all that kind of stuff, that's a different story. But I do think that's a real thing. Look at the Green Revolution. You can't look any further than the Green Revolution. So go Google the Green Revolution and see, if it weren't for the Green Revolution, I mean, population of Africa would be a fraction of what it is today. Probably the population of the world would be a fraction of what it is today. It was literally a revolution in agricultural capability. Well documented. I read that the cod needed some sort of wayfinding when the older fish were killed off, the English was not functioning as before. Okay, good point. Neolithic urges, immune institution, technology of gods. Sure. Maybe we need some sort of like spiritual awakening. I don't know. That's Donald Trump's job. Neolithic urges, medieval institutions, and technology of the gods. That sounds like Donald Trump. Anyway, so hopefully this was useful. Covered a lot of territory, but it's all good stuff and legit. Like, this is not fictional stuff. This is real stuff. So hopefully it will be helpful for you as you chart your path forward. So if there's not any more questions, I will sign out. Yes.
Is it okay if you could stay back just for a couple of minutes?
Sure.
Okay. Mona,
Okay.
by the way.
Rock on, Jen. Okay, so I'll stop recording now.
Okay.